So very good afternoon to all the participants and good afternoon, Shriram sir. So shall we start?
Yeah, good afternoon, sir. Okay.
Yeah, 2 minutes. I'll just make you presenter as well as. So let me. It gives a pleasure to introduce our resource person of this session, Dr. Shriram Dubey. He has been with the Indian Institute of Information Technology, IIIT Allahabad, since July 2021, where he is currently the assistant professor of Information Technology Department. He was earlier with the IIIT Sri City as an assistant professor from December 2016 to July 2021 and research scientist from June 2016 to December 2016. He received the PhD degree in computer vision and image processing from IIIT Allahabad in 2016. Before that, from August 2012 to February 2013, was a project officer in the Computer Science and Engineering Department at Indian Institute of Technology, Madras. Currently, Dr. Dubey is executing the research project funded by Global Innovation and Technology Alliance, India-Taiwan project. He has also executed the projects funded by DRDO Young Scientist Lab in Artificial Intelligence and SEP. He was a recipient of several awards, including Best PhD Award in PhD Symposium, IEEE CICT 2017 at IIITM Gwalior, and NVIDIA GPU Grant Award twice from NVIDIA. He received the Outstanding Certificate of Reviewing Award from Information Fusion elsewhere in 2018. He also received the Best Paper Awards in IAPR, CVIP 2020, and IEEE UPCon 2015 conferences, which are considered to be the most prestigious conferences in image processing and computer vision. His research areas include computer vision and deep learning. With this short note, we are really glad to immediately accept our invitation and ready to deliver the session, sir. Over to you.
Thank you very much, sir, for the introduction. And thank you very much to all the participants also for participating in this IIIT, which is sponsored by IICT on data science and its applications, organized by Computer Science Department, Central University of Tamil Nadu. So a very congratulations for the organizer to basically conduct such workshop, which is going to be very much beneficial for the faculty members. So as I already introduced, basically this talk is going to be on introduction to deep learning and convolutional neural networks. So basically we will have in two parts. In the first part, first I will go through briefly that, okay, what is the basics of this machine learning, and then leading to the development of deep learning and a special type of deep learning model, which is used generally to deal with the image and video type of data, that is convolutional neural network. So introduction of that. So is it audible, sir?
Sir.
Sure. Okay. So coming to basically the institute where currently I am working, this is IIIT Allahabad. So this is one of the research-led institute, and that also has this institutes of national importance. And basically, we have the departments like IT department, electronics department, but we have a master's program which is very much focused and specialized, like we have in the robotics, we have in human computer interaction, we have in data science, we have in machine learning. So apart from BTech, all other programs are very specialized. So basically I belong to computer vision and biometrics lab here at IIIT Allahabad, and which basically executing the projects which is funded by reputed this funding organizations, either DRDO, DST, SR, MHA, DITA, and even currently we are executing 3 international projects basically as a lab, which is between India, Germany, India, Slovenia, and India, Taiwan. So we are also going to launch a new conference that is International Conference on Computer Vision and Machine Intelligence. This is going to happen in August 2022. So very soon we are going to float call for papers, and I will be happy to share the call for papers to the organizers as well, and I will request that they can also share with all the participants. So as far as this particular talk is concerned, so machine learning basics, introduction to deep learning, where we will basically have a look that, okay, how this deep learning has evolved and what is the basic difference between machine learning and deep learning, and some main components of deep learning models, which includes some hyperparameters and functions which is used, like activation functions, optimizers, cost functions, how we can train deep learning model, what are the typical regularization methods, how we can perform the tuning. So these things, and then a quick introduction of convolutional neural network. So in case if you are getting any issue or you are not able to get anything, you can stop me at any point of time and you can ask the question. So now if you see, this machine learning has been a very prominent as well as widely adopted technique in order to deal with the different type of data. So we have different models for the machine learning that can be categorized into supervised and supervised. So we'll come to that. But ultimately, what we want to do through any machine learning algorithm, we have some data with this. Now we want to learn machine learning algorithm using that data. That data might be labeled data or unlabeled data. So let's right now focus over the labeled data, then, because it will be easy to understand. So suppose if we have the labeled data in the sense that along with the data, we also know that what we want to predict from that data. That is basically the training part of the data. So now using machine learning algorithm, what we want to do, we want to basically learn the important characteristic from the data, which can lead to what prediction we want to make. And once our model is trained, then we can use that trained model. Basically, this is kind of a generating the knowledge or mining the knowledge from the labeled data that we have based on, this is my data, I want to produce this thing. So basically, what could be the mapping? So this is also kind of a mapping from the data space to the label space. And once we have this trained model and we are getting labeled data at prediction time, then using the trained model, we can basically generate the class labels and prediction if it is a classification problem. If it is some other problem, so based on our problem, we can generate the corresponding output. There are different types of learning. So this is very common thing, and most of you might be knowing. I will just go through quickly. So supervised, where we also know that what we want to predict. So in that particular case, basically, along with the data, we also know our output space. And then this is kind of a typical mapping from our input space, which is the data, to output space. And we want to basically learn that mapping. Unsupervised, in unsupervised learning, we do not have any label given to us. In that particular case, basically, we need to exploit some characteristic between different instances of the data, means some similarity, dissimilarity, or by any other mean, we can find out the different characteristics such that we can infer some information from that data. There are many other supervised, basically other mode of supervision which can be classified in between supervised and unsupervised. Like we have weakly supervised, we have pseudo supervised, we have self-supervision. So all these things can be categorized in between supervised and unsupervised, where we have some sort of supervision, it's by some mean, but that might not be complete supervision. But if we talk about supervised and unsupervised, then these are the extremes. Other supervision modes can be in between that. There is a reinforcement learning also. That is also one of the way of learning, which is mostly useful in the robotics area, where basically we want to learn from the reward function. So basically it is based on the reward function. So we can have typical problems like there is a classification problem, or a regression problem, the clustering problem. So if you see this clustering problem, this can be unsupervised learning problem. Suppose we don't know that in which cluster data belong, but we want to find out, we want to divide my data into 3 clusters or 4 clusters. So in that particular scenario, it will become unsupervised problem. And when we are talking about a classification problem, suppose if I have some data that I want to classify into some category, and for our training set, we already know what are the categories, then this is going to become the supervised problem. So either it is machine learning or deep learning, everywhere these learning modes are going to be very similar. We are going to have supervised.
Shivaram, so you got muted, I think.
Now is it fine,
Yeah,
sir?
yeah.
Okay. So we are also going to have these types of learning mechanism in machine learning as well as deep learning both. So just a quick recap that what are the basic classifiers in machine learning techniques that generally we use, like nearest neighbor classifier, where we just want to find out the nearest sample in our training data. And then based on that, we can just find out, okay, what is the class label of the nearest sample? That class label can be also given to the test example. So this is a very simple this classifier which is utilized in many scenarios. K nearest neighbor, where instead of just relying on the nearest neighbor, we can rely on 5 basically key number of nearest neighbors, and then we can perform a majority OT, because when we are considering more than one number of nearest neighbors, then it is also possible that we may get the nearest samples from different classes. Then we can basically find out the majority OT, and we will associate the class label to the test example based on which particular class is in the majority among the k number of nearest neighbors. There is a linear classifier. So linear classifier is trying to distinguish the data distribution that we have into two categories. If it is a two-class problem, suppose if we have n-class problem, then the same concept can be extended even for the multiple classes. But the basic idea is to find out a hyperplane. So now if you see the data, you can always visualize in some d-dimensional world, because whenever you have the data, then data is generally either in the vector form or it is in the matrix form. So there are different ways we can basically represent the data. Suppose if this is image, then we can represent image in a matrix form. But if you have the data, suppose if you have the NLP data or the speech data, then we can represent basically in the temporal manner. Even we can also have the data. Suppose you want to develop a system in order to basically find out the fault tolerance. Then in that particular scenario, even we can have a vectorized data. Now, how many number of values we can have in the vectorized data? It completely depends upon the scenario from where we are getting the data. So let's assume that if your data is represented into d-dimensional world, so basically here, even if you're just seeing either a red circle or this blue square, but actually this is representing the data in d-dimensional world. So it is having d number of values. So in that particular scenario, so if our data is represented into d-dimensional world, then in case of the linear classifier, we need to find out a hyperplane in d-dimensional world. So, but that hyperplane we can always represent in this notation like w dot x. We can think w as a vector. X is our input data, that is also a vector, and then we can perform the dot product. So once we know that what is the equation of this hyperplane, equation of the hyperplane means we know what are the values of these parameters, that is w, because w is a vector. So it will have w1, w2, w3, like up to wt. So then our task is very easy. And in fact, this concept is very much useful, because even nowadays, what we are doing in deep learning, we are still utilizing this very basic concept of this linear separability between the classes. We can extend this particular concept to even the multiple classes, where we suppose if we have 3 classes, then we can say, I'm going to have basically 3 hyperplanes. So I'm going to perform one class versus the rest of the classes binary classification, and based on that, I can basically compute the class scores. And based on highest class score, my example can be categorized into one of the classes. So now here, a very important thing, which is also related to the deep learning, that even in case of the deep learning also, we are going to have the parameters. And entire machine learning, entire deep learning, and even if you see the data science is actually dependent upon the optimization. So basically what we are trying to do, everywhere we are trying to learn a mapping function. That mapping function can be either a machine learning uh, basically algorithm, or it can be a deep learning algorithm, or any algorithm. But ultimately, we are trying to learn a mapping function from input space to some desired output space. Why I'm saying desired output space? Because for the same input, we might want different output in different scenarios. For example, suppose even if I have a lot of faces, then I can also have a system where using this face I can predict the age of the person. I can have some other system using the same face. I can predict the gender, male versus female, or I can predict the facial expression. So even for the same data, I can produce multiple outputs using different systems. So that's why basically this is kind of a mapping from input space to some desired output space. And in order to do this mapping, we want to basically have some parameters through which we can perform the fitting of this particular mapping. But what should be that parameter? That is the main question. How we can find out those parameters? Either it is machine learning or data science or even deep learning, everywhere, the main problem is to find out the right set of values of these parameters. So now if you are talking about deep learning, we will see shortly that we will utilize gradient descent optimization technique in order to find out the right set of values. But if we have some set of values, parameters with us, then we can always measure how well it is performing or how bad it is performing. So for example, even in this particular scenario, if this first row is representing a classifier, that is for the cat category, cat versus rest. Second row is representing a classifier for the dog category. Third row is representing a classifier for the sheep category. So now we can, and in the present set of values of the W, we are getting the highest class score for the dog category, but we have input image from the cat. It means that at present, this W is not suitable for this particular example, or it is not. Hello.
Yes, sir. I'm.
Yes, sir.
It seems there was some problem, sir.
Sir, you
You got
disconnected.
disconnected.
Okay. So can you give the share
Yeah,
permission?
I'm doing that. Yeah.
So I don't know
Yeah,
where I
here
was at.
just a minute before you got disconnected.
Okay, fine, sir. Okay, so basically, by utilizing this particular strategy, one versus rest of the category, we can also utilize the classifiers for the multiple classes. And even a very well-known machine learning mechanism, most of you would be aware, the support vector machine, which is very common. So support vector machine is trying to not just finding out the uh, hyperplane. Along with that, it also want to maintain the maximum margin between the nearest sample in both sides, basically in distribution of both the categories. So this is modeled in the objective function of the support vector machine, and based on that, the entire hypothesis is built upon. So now let's quickly come to this machine learning versus deep learning. So now if you see here in practice, when we are going to use machine learning techniques, then what we used to do. So first we transform our input data into feature space, and that is a manual process. So we used to identify that what should be the right way of extraction of the important features. Now, this is completely subjective that what features are going to be important. In traditional machine learning approaches, we as an expert are basically we manually used to identify those features, and then we used to develop the algorithm to code those features into vector form or basically into feature representation form. And once we have extracted the important features that we feel that this is important for this problem. For example, suppose if someone wants to perform the facial expression recognition, then if we want to find out what features might be important, then someone can say that, okay, if we take the features which is nearest to the mouth, which is nearest to the eyes, then what is the movement of this visual, what is the movement of this visual appearance while people are giving the expression, that can be a great feature in order to decide on this facial expression recognition. Now, so what we can do, so manually we can now look basically these eyes and mouth features, and then we try to extract basically what is the relationship between the pixels that is surrounding this mouth and this eyes region. So like that, we used to identify the features manually, extract the features manually, and then we were using that feature to train the machine learning model. So this was a two-step process where in the first step, we used to identify the feature, and then in second step, we used to learn machine learning technique. But what is happening in case of the deep learning? So what transition has happened from machine learning to deep learning? This manual extraction of feature part, this manual extraction of feature is also automated using neural network. It means that what feature is important, let's network itself to figure out, network to learn that what features are important. It will extract those features automatically. And now it might be a little bit difficult to understand at this point of time that how network can figure out what is the important feature. So again, network can identify what is the important feature using the optimization technique. So basically in deep learning, what we are going to do is to initially the performance of our deep learning model will not be very good. When we are going to train the deep learning model, then performance will be very bad in the initial iteration. Why? It will be very bad because initially the parameters or the weights which is present in any deep learning models are initialized randomly. In that particular scenario, whatever final features that is produced that is generated by this deep learning model, that is also random. And in that particular scenario, it is going to give you the random output. And when your deep learning model will give the random output, then basically performance will be very bad. But that's what is the optimization in the deep learning, that okay, performance is bad, but now what we should do such that performance should improve next time if I train. So that's where the training of this deep learning model is going to happen in an iterative fashion. Means we will train these deep learning models in multiple epochs. So, and every time we will try to improve the parameters with a guarantee in such a way that will give us the guarantee that the performance will improve next time. And why this is a guarantee? Because we will utilize basically this gradient descent optimization technique, which is based on the minimization of the error of our deep learning model. But so now, so ultimately, what is deep learning? So the deep learning is the technique which can learn the important features automatically from the data, along with performing the final objective that we want to do. If it is a classification, it will do the classification. We can have one basically classification layer at the end. Suppose if you want to perform kind of a regression task, then we can, our basically model will be designed in such a way that last layer is going to produce such output where we can perform the regression or any other objective function we can have based on the requirement. But ultimately, is there any question?
No, it was it.
Okay, sir. But what is the most important thing in deep learning is Now we don't
I request the
require
participants to keep your
to
mic
figure out the important features manually, because in manual extraction of the features, there are the chances that we cannot figure out what are the most important features which can contribute towards the better performance of the system with respect to problem that we are solving. Now here you can see this graph is providing the interest of the researchers in machine learning and deep learning domain. So here you can see after 2008 and 2009, there has been a huge growth in the research that is happening in machine learning and deep learning area. And basically this is considering the global scenario. It is globally, the interest in machine learning and deep learning has been increased drastically, or it is basically has gone exponential, especially in past 1 decade. And why this has happened? Again, because deep learning model is end-to-end trainable model. Means we don't need the systems in different stages. We don't need the first feature extraction manually and then learning again machine learning models. Rather, we can have just one model which can be trained in end-to-end fashion, where we can give our raw data as the input directly to that system. And that was basically cumbersome in case of the traditional machine learning, and which is feasible in case of the deep learning, where we can give the raw image or the raw data as a feature to the model, and the model will produce the final output directly. But in between, we will have a hierarchy of layers. Why hierarchy of layers? Because this deep learning model is built upon this neural network, and neural network itself is having its different types for the different type of data. So for example, if you have a vectorized data, then you can use multilayer perceptron, where you can have a deep learning model. You can have a deep neural network. And suppose if you have image or video data, then you can use convolutional neural network. If you want to work with the NLP problems, then you can utilize recurrent neural network based models. Even if you want to do some generative tasks, you can use generative adversarial network model. So there are different variants of these neural networks based on what is the type of data that we have in hand that we want to deal with. So again, this is deep learning is state of the art in speech recognition. So in case of the speech recognition, so first deep learning started giving outstanding performance in speech recognition around 2008. So around 2008, basically this deep learning words started coining, and first in the speech processing, and several big improvement that has happened. Basically, this is in NLP. That has happened and utilized basically these deep learning models. As far as computer vision is concerned, so from 2012, these deep learning models is starting playing the game in computer vision, and nowadays computer vision cannot be imagined even without deep learning, because roughly 99% of the research which is happening in computer vision area is actually based on the deep learning model. Or in other words, we can also say that most of the developments which are happening in deep learning, they are also happening through the computer vision applications. So from in 2012, first research came which utilized this convolutional neural network and gave outstanding performance. That was basically this AlexNet model, and that too on this ImageNet large scale visual recognition challenge, which is kind of a computer vision World Cup. Means people are basically just trying to get better and better performance on this particular challenge, or in using this particular data set. And not just speech recognition or computer vision, even in NLP also. This interest or the growth in deep learning models, there is a huge growth that has been observed, and especially in last 5 years. So if you talk about NLP, then in last 5 years, huge growth has happened, and these models like LSTM and then this GRU, RNN models, and now these transformer models are there, BERT. So all these models are basically very, very, very popular. And that too, these models are coming from top these technical industries like Facebook, Microsoft, NVIDIA. So all these basically industry people, they are working on this, and they're also doing research and development. So now let's go a little bit technical. So these deep learning models are built with neurons because we have this neural network, which is we have many number of layers in neural network. What is meaning of many number of layers? We will come to that in a bit. But what is a perceptron? So perceptron, we can think a smallest computational unit that can basically take some data as the input, and it will have some parameters and it will perform some computation. So it is still a little bit generic, but here the computation that we would like to do through the perceptron is linear in nature. So basically we are simply doing this W dot X. It means that we have some input coming in, which is represented as X1, X2 up to XD if we have D-dimensional data. Then we will also have our weights or the parameters, which is represented by W1 to WD. Then we will basically take the dot product between these two vectors, and there is a bias term will be added. If you're talking about a perceptron, then perceptron is having a sign function on top of this computation. So if this is leading to greater than 0, then basically it will convert it into 1. Otherwise, it will convert it into -1 or 0 based on what hypothesis you are following. So we can also use a single neuron as a linear classifier. So what we can do, so in this particular perceptron, if we remove the sign function, so instead of sign function, now we can think of any generic function, any function that we can attach on top of this W dot X plus B, then it will become a neuron. And that particular function that we will attach here will become the activation function. So suppose if we just use sigmoid basically as the activation function, then a single neuron can be treated as a binary softmax classifier, which is also termed as the logistic regression. And it can produce, because if you're aware with the sigmoid function, then sigmoid function converts everything in between 0 and 1. Then the output is always going to be in between 0 and 1, and everything in between 0 and 1 we can treat like a probability. So we can say that a single neuron as a linear classifier can produce the probability of being classified into one of the categories. So basically whatever we are producing can be treated as a probability for one of the classes, and if you take one minus of that, then it will become probability for some other class for a binary classification. So these neurons are also inspired, not completely, we can say lose inspiration from the human neurons. So here you can see, in case of the human neurons, basically we have the nucleus. Nucleus is taking the impulse, which is basically coming from different nucleus through the dendrites, and then it is doing some sort of computation. What computation exactly this nucleus is doing, that is still black box. But then it is generating the impulse, and that impulse is given as the input to other nucleus, which is in the nearby region. So motivated from this particular concept of human neurons, this neural network is also proposed. Now in neural network, we are going to utilize more than one neurons, and then neurons will take the input from the different neurons, and whatever output is produced by a neuron can be treated as the input to the next set of neurons. So that's where now we are going to have a neural network which is going to follow a hierarchy of computation. So here you can see this is a typical neural network with one hidden layer. So we have the input. Now this is the hidden layer. In the hidden layer, now we have here 4 neurons. In the output layer, we have 2 neurons here. And in case of the artificial neural network, a particular neuron is going to receive the input from all the neurons in its previous layer. So for example, if this is the first hidden neuron, then it will receive 3 inputs. The same 3 inputs will be given to other neurons also in the same layer. But a neuron in a given layer will take the input from all the neurons in its previous layer. So here you can see, if you consider output of a neuron of the output layer, then it will take the input from all the neurons in its previous layer, which is the hidden layer here. So we have 4 hidden neurons, then 4 inputs will be received by these output neurons. And then we have that many number of weights also, other parameters also for each neuron. So mathematically, it can be written as for the function of hidden layer, h is equals to, this is the sigmoid function, which is treated as the activation. And these are the weights. So these weights are basically, it is going to be d-dimensional based on how many number of entries we have in our input. So for example, in case of the hidden layer, this is going to be having 3 values, W1, W2, W3. In case of the output neurons, we are going to have 4 values because we are receiving 4 inputs. So we can go beyond one hidden layer. We can have 2 hidden layers. So for example, you can see this is a typical example of 2 hidden layer in a, and then this is going to be treated as a multi-layer perceptron or multi-layer neural network where, but in case of the multi-layer perceptron, if you take a neuron in any given layer, it will take the input from all the neurons in its previous layer. So this is basically the underlying concept which is utilized in this multi-layer neural network. So now this is going to be a hierarchy of computation. So like that, suppose if I am going to have 50 number of hidden layers, hidden layer 1, hidden layer 2, hidden layer 3, and we can have even suppose 50 hidden layers, 100 hidden layers, 150 hidden layers. So if you are going to increase these number of hidden layers more and more, then your network will become deeper and deeper. So this concept of deep learning has come from this perspective that when we are going to have many hidden layers, then the computation of the data that we are basically doing here is going to happen in a hierarchical manner. And it is not just hierarchical manner, it is going to be hierarchical computation at a different level of abstractness. So this is most important thing in case of the deep learning, which has been observed that if suppose if you are going to have 50 number of layers, hidden layers, then the early layers tend to extract very primitive features. But if you go in the later layer or the deep layers tend to extract very abstract level features. So it means that this now we can also visualize this entire deep learning models from a different perspective, from the projection perspective. So now what we can say that ultimately we have some training data with us. Suppose if my training data is very simple, it's simple in the sense, suppose if I have 2 categories and all the instances that I have in one category, all the instances that I have in another category, if these 2 categories are very well distinguishable, then there is no need of deep learning model at all. Then even you can just have a simple linear classifier and it will work very well. It means that it is not required to use deep learning always. Then we need to understand that where this deep learning is going to be helpful, because deep learning is also kind of an extension of the linear classifier that we had by including some non-linearities into this entire pipeline and doing this basically projection in the stages are basically in a hierarchical fashion. But ultimately, now we have some data. We want to transform the data into the output space. And if our task is very easy, then we don't need even the deep learning model. Or even if we are using a neural network model, then we don't need a very deep neural network. Even if I have only 1 hidden layer or 2 hidden layer, that might be sufficient for our problem. But where this deep learning is going to come into the picture, where we need more and more number of layers if our data is going to be complex. Now, how we can define the complexity of the data? So suppose if I have 2 categories, suppose I have cat versus dog. Let's just assume from the images, because it is always easy to visualize the things from the images. Suppose if I have a lot of images of the cat, I have a lot of images of the dog, but it is also possible that many images of the cat is kind of a taken in very difficult scenario, or the scenario where it is not completely visible, or even we have some cats which is looking like dog, means even as a human being sometimes we may get confused. Then what is going to happen in that particular scenario, that these two categories are not going to be very easily distinguishable. When these two categories are not going to very easily distinguishable, in that particular scenario, what we need to do? Now we need to transform this data into some higher order space where we can do this separation very easily. So if you're talking about a traditional machine learning pipeline, we used to perform the same task there. The manual extraction of feature was actually doing the same thing, because if you are extracting the features manually, then basically we are trying to distinguish one class from other classes in some higher level feature space. So even if we have this deep learning model, then slowly what we are trying to do here, so we are having one layer, second layer, third layer, fourth layer. Then once my data is processed from the first layer, and if I try to visualize my data, then what is going to happen? Because now this is going to be in a feature space, then the separability between the data of different categories will improve. And if I go even after the second layer, then it will further improve. If I go after the third layer, it will further improve. And suppose if I have 50 number of layers in my deep neural network, then if I try to visualize the features, there are different visualization tools, like you can visualize through Tishni. So Tishni is one of the great visualizer where you can visualize that, okay, what is the distribution of your actual data that you have, raw data that you have, and what is the distribution that you are getting in the feature space. You can take the feature from any of the layer of your neural network model, and you can try to visualize through this Tishni, and then you can see that the distribution that you have in the raw space, that is going to be very much kind of a mix. I will show one demo also using some online tool, that where data will be basically kind of a mixed, means it is not going to be linearly separable. Then in that particular scenario, we can basically learn the decision boundary, and that decision boundary can be non-linear. Basically, that is equivalent to projecting our data into some higher order space where the abstractness is going to be increased with respect to what problem we are solving. And with respect to that, we are going to have very abstract feature. It means that now we are also going to use the classifier, even in case of either it is neural network or convolutional neural network. If it is a classification problem, the classifier that we were using with the machine learning can be also used with the deep learning, because the last layer that we are going to have in deep learning models, this is also going to be based on what exactly what we want to do. Rest of the layers can be treated as kind of a feature extraction techniques with increased level of abstractness if we go from left to right in this deep learning hierarchy. So now let's come to just some computation of the number of neurons and learnable parameters that we have. So now here I have two neural networks. In the first neural network, only one hidden layer is there. However, in the second neural network, we have two hidden layers. In the first one, the number of neurons, we will not count the input layer. Then this is going to be 4 plus 2, 6. However, the number of learnable parameters that we can compute based on what is the number of inputs that we are receiving, because for each input, we will have one parameter. Then only we can perform this double dot X. So it means that for the first hidden layer, if you talk about one neuron, then it will receive 3 inputs. It means 3 parameters will be there and one bias. So 4 parameters for one neuron. We have 4 neurons here. So 4 into 4, 16 parameters will be there in the hidden layer. If you're talking about the output layer, so one neuron of output layer receiving 4 inputs, then 4 parameters plus 1 bias, that is 5. And 2 neurons are there in the output layer. So 5 into 2 is 10. So this is going to be 10 plus 16, total 26 number of parameters, including bias. If we exclude the bias, then this is going to be only 20 parameters. Similarly, we can compute for the second also. The total number of neurons will be 4 plus 4 plus 1, that is 9. And total number of parameters, again, we can compute. It will come to 41. So now then, again, most important question comes. Now we basically got to know that this deep learning can learn the features automatically, and we can have some objective function, and all these things are, and this is going to be very flexible. This is an end-to-end learnable models. Everything is there. All these are very good things. But main question comes here, that how we can train a deep learning model, how we can train a deep neural network. So what is the training procedure that generally used generally used with these deep learning models. So the training procedure is that we cannot use the entire data set for the training if you have a large scale data set. If your data set is very small, then even you don't need deep learning models. You can directly use these linear classifiers, or even with you can use the features of some pre-trained deep learning models, and you can use machine learning classifier on top of that. You don't need to train the deep learning models if you do not have the large scale data set, because training deep learning model requires a large scale data set, as we have many and many number of parameters in the deep learning models. But what is the training procedure? The training procedure is we will now we will randomly sample some data that is called the batch of data. Using that data, we will do the forward computation that is called a forward pass, and we will compute the error. So error will be computed based on some objective function. For example, if you are doing a classification problem, then you can utilize the cross entropy as the objective function. Then we can compute cross entropy loss as the error. And based on that, now we need to, so this error is actually giving us the goodness of our model at present. Why I'm saying at present? Because what are the values of the parameters of the model? Those values might not be very good. Then in that scenario, our error might be high. So what we want to do now, we want to update the parameters of the model in such a way such that if I'm going to perform the forward pass again next time, then the error should decrease. And that's what called basically the back propagation. Means first do the forward pass, compute the error, and now do the backward pass. In the backward pass, now we need to update the parameters of the model. And this update is going to happen using gradient descent optimization technique, where we are going to update the parameters in the opposite direction of the gradient. Because if you update the parameters in the direction of the gradient, then this is a maximization problem. Then it is going to maximize the error function, but we want to minimize our error. And because this is a minimization problem, then we need to utilize the gradient descent, where we need to update the parameters in the opposite direction of the gradient. It means that what is going to be very crucial here, how to compute the gradient of our objective function with respect to any parameter. So if we can do that, then the training of any deep neural network model is going to be very easy. But then this is just simple update. And what is the update? Update is, suppose if W is the parameter, then W is equals to old value of W minus there is some learning rate multiplied with what is the gradient. But now question comes, how we can compute the gradient. So here you can see, so this is a very nice visualization using different optimization techniques. Like SGD is called stochastic gradient descent. Momentum is stochastic gradient descent with momentum. There are other versions also. Nowadays, Adam is very popular, but Adam is not present in this particular diagram. That's not an issue. So here you can see. So what is happening? If you see these basically, if you see from where these lines are originating or these curves are originating, that is the initialization. It means that when I'm going to start the training, before that I need to initialize all the parameters, then only I can update it next time. So generally initialization happens in a random fashion. So now, so this is the initialization. So initialization means now all the parameters are initialized randomly. And now if you consider all the parameters all together, then we can think all the parameters all together just as a point into some d-dimensional world if d number of parameters we are using in our network. So now, and this is this particular entire plot here is actually representing this loss landscape. Loss landscape means that okay, how our loss function is going to behave, or what is going to be basically kind of a landscape in which our objective function is going to be updated. And based on these different optimization techniques, some optimization techniques can be faster, some can be smaller based on the characteristic. So that's where you can see some optimization techniques are able to converge very fast. So even you can see kind of RMS prop here. If you see, this is converging very fast, and AdaGrad also is converging very fast as compared to these other optimization techniques. So in gradient descent, we used to update the weights in the opposite direction of the gradient. So this is basically written in kind of a pseudo algorithmic form. So here you can see weights plus is equals to, so this means weight is equals to weights and minus step size multiplied with the gradient information. So this is the most important thing, how to compute the gradient. So most of you are well aware that what is this gradient and how gradient can be computed. But question comes here, how we can compute the gradient in neural network? Because in case of the neural network, especially if it is a deep neural network, we have many number of layers. And now suppose if a parameter is present in layer number 2, how can I compute the gradient of the final objective function with respect to this particular parameter? So you are well aware with the chain rule, which is basically the way we can compute this gradient in a backpropagation manner. So if we have basically a complex function, then we can always break the function in a sequential manner, and we can break the function in a sequential manner, then we can apply the chain rule in order to compute the gradient. So we will take a quick example here. For example, suppose if my function is x plus y, I can easily compute this del f by del x, that is a partial derivative, that is going to be 1 here. If this is x into y, then also we can compute it very easily. So del f by del x is y, del f by del y is x. Okay, so here is a question. So suppose if my objective function is fxy is equals to max x comma y, where x and y are the inputs to our function, then what will be the value of del f by del x and del f by del y? And such type of functions may come in our basically this deep neural network. And in fact, there it is there. So we have kind of a max pooling layer, which is very common to use in any deep neural network models, that we need to basically perform. We need to compute the gradient there. So the answer here is, if del f, we need to compute del f by del x, then this is going to be 1 if x is greater than or is equals to y. Otherwise, it is going to be 0. Similarly, del f by del y is going to be 1 if y is greater than or is equals to x. Means if the max is producing y, then del f by del y will be 1. Otherwise, it is 0. So we can have the always complex expression or compound expression. So suppose if we have the expression like x plus y into z, then we can write this as f is equals to q into z, where q is x plus y. Now, what I want to show here, I am interested to compute del f by del x, del f by del y, and del f by del z. But what we can do actually, if we can compute del f by del q, then it is very easy for us to compute del f by del x and del f by del y, because we can easily compute del q by del x and del q by del y, because q is directly dependent upon x plus y. So we can compute del q by del x is 1, del q by del y is also 1. And if we can find out the del f by del q, then I can apply the chain rule. And what is that chain rule? The chain rule says, if I would like to compute del f by del x, then this is nothing but del f by del q into del q by del x. So using this chain rule, if I can get del f by del q, which is very easy to compute, del f by del q, that is z, and del q by del x, which is again easy to compute, that is 1. So it means that using chain rule, so what we can do now? Now I can compute the gradient of my objective function with respect to the parameters of the last layer. And once I have that gradient, then that gradient we can utilize to compute the gradient of objective function with the parameters in the second last layer. And then whatever gradient we are getting there, now that can be utilized to compute the gradient of objective function with respect to the parameters in the third last layer. So it means that now we can utilize already computed gradient in the third last layer to compute the gradient for the fourth last layer. Then again, we can utilize the gradient already computed for the fourth last layer to compute the gradient for the fifth last layer. So like that, we can basically do the back propagation. So that's why this entire technique is called the back propagation. Means we are back propagating the gradient from our last layer to the first layer using this chain rule. So the same thing can be represented in a computational graph here. So we can also have some inputs like -2, 5, -4. It can, this is the forward pass. So it will compute 3 here, q is equals to 3, f is equals to -12. Now when I'm going to perform the back propagation, suppose if I am back propagating unit amount of the gradient, then what gradient is going to be received by this x, y, and z? Then first we need to compute that, okay, how much gradient will pass through this q and how much gradient will reach to the z. So because this is a multiplication function, f is equals to q into z, then what we need to do? So this 1 will become the running gradient. And now what is the local gradient? So del f by del q is the local gradient, which is nothing but z. And the value of z is -4. So -4 into 1 is going to become the basically the gradient here, that is -4. Similarly, if I want to compute del f by del z, then del f by del z is going to be q, and the value of q is 3. So that is going to be multiplied with the current running gradient is 1. So 3 into 1 will become 3 here. Similarly, I'm interested to compute del f by del x, but we already have in hand del f by del q. Del f by del q is -4, but I want to compute del f by del x. Then we can utilize the chain rule. Del f by del x is equals to del f by del q, which is -4 multiplied with del q by del x, and del q by del x is 1. So it means -4 into 1 will become -4. And the same thing is going to happen with y also. So this is a very simple procedure of backpropagation to backpropagate the gradient from our last layer to the first layer. And once we have the gradient here, then we can update the parameter using that gradient. And because we are updating the gradient, we are updating the gradient in the opposite, we are updating the parameters in the opposite direction of the gradient. It means that this is going to do the minimization of our error function next time. The same concept we can utilize even with this function also, where we have a max operator. So multiplication, then max, then plus. So this is 2 minus 1, max will produce 2, 3 minus 4. This multiplication will produce -12, -12 plus 2, -10, -10 into 2, -20. So if I am going to backpropagate unit gradient here, so now if you see what could be the local function here, which produced -20 from -10, this is actually nothing but 2 times. So this is kind of a function like y is equals to 2x. Then what will be the local gradient here? Local gradient will be 2. It means that local gradient is 2, running gradient is 1. Then the running gradient will become 2 here. So now we have a summation, and summation is always just going to basically distribute the same running gradient in all the branches. So basically it will become 2 and 2. So now here we have multiplication. In case of the multiplication, we need to multiply with another one. That's what will come, because if you have y is equals to xz, then del f by del x will become z, and del y by del z will become x. So basically it is going to be opposite. So 3 into 2 will become basically 6 here, and -4 into 2 will become -8. But what about this max? So as I mentioned earlier, that whatever is the max, that will get local gradient as 1, otherwise local gradient is 0. So the local gradient for z will become 1. So 1 into running gradient 2. So it will become 2. And for w, it will become 0 because -1 is not passed through this max function. So now, basically, this is the way we are going to train this entire deep neural network models. Now, another question comes that what is the role of the activation functions? Because we have seen the activation function in these neurons, because neurons are doing this sort of computation, and then it is applying an activation function on top of that. And this is basically the super important thing of the entire this deep neural network, because if we do not have this activation function into deep neural network, then the deep neural network is no more deep neural network. It is just a single layer. It means because if you see a neuron is doing sort of only linear operation, w dot x plus b, everything is linear. Now, if I'm having a linear function, if I apply one more linear function on top of that, then one more linear function on top of that, then the entire thing is just a linear function. Then instead of writing that 50 times, I can just write only single linear function doing exactly same task. It means that if you do not have any non-linearity in your deep neural network, then the entire deep neural network is nothing but just one linear function, and then that is not going to be of any use. That is not going to be of any use. So that's where the expressive power that we are getting in our deep neural network is actually due to involvement of non-linear layers in our deep neural network. And generally this non-linearity is introduced in deep neural network using this activation function. So what, and even here you can visualize also. So suppose if I have less number of neurons, then I will have less number of activation function as well, because whenever I have a neuron, then I will have one activation function with that neuron. Then the expressive power of our neural network will be limited. It will not be able to learn the non-linear decision boundaries very well. So here you can see this is a data distribution which is non-linearly separable, because you can see some red dots coming in between the blue green dots, and even some green dots coming in the distribution of the red dots. It means that this data is not linearly separable. Then in that particular scenario, our model should be able to learn a non-linear decision boundary. Then only we can distinguish these two categories. But if we are having less number of neurons, in turn, if we are having less number of non-linear functions, then this is going to be the power is going to be much lower. But if we increase the number of neurons, for example, here you can see if I have 20 number of neurons, then in that particular scenario, I'm going to have 20 activation functions, means 20 non-linear functions. And then the basically non-linear capability, means transforming our data through the non-linear system, is going to be increased. And then basically our system can learn even more complex non-linear this boundary or decision boundary. So we have many activation functions existing. For example, sigmoid is one of the popular activation function which was being used long back, but this sigmoid is having some major issues, like when an input is very small or very high, then it actually saturates, and the gradient in those regimes are going to be quite low, and that is very near to zero. If you see this particular region here and this particular region here, then this is complete kind of a flat, then the gradient will be close to zero. And if gradient is close to zero, then what will happen in entire chain rule? If something coming as zero, it will basically going to influence all the updates of the parameters coming in. So that's where this is going to be problematic. So there is another activation function tanh that also became very popular. And in fact, this is very popular for recurrent neural network models. But it is very similar to the sigmoid, but instead of having the output in between 0 and 1, it will have the output in between -1 and 1. But the major problem of sigmoid is also existing with this tanh activation function. Coming to the activation function, which is very popular nowadays, is actually this rectified linear unit that is called ReLU. So this activation function is very widely adopted, especially in deep learning models, because so the sigmoid and tanh, it is going to be much more problematic if you have deep neural network, because in deep neural network, the computation of your gradient is dependent on many layers through which gradient is backpropagating. And if anywhere your local gradient is close to zero, then it is going to influence the entire thing. So that's where this is going to be much more problematic. So this ReLU activation function became very popular. ReLU also has problem, but it has the problem only for the negative inputs. For the negative inputs, it produces zero output and gradient is also zero. So ReLU also suffers from the vanishing gradient problem, but only for the negative inputs. But at the same time, this is much faster because it doesn't involve any complex function. This is just a two linear function. So this is going to be less expensive. That's why this is very widely adopted in deep neural network or deep learning. Even nowadays, there is a trend of having the adaptive activation function, where activation function can adapt its shape based on the requirement. So the Swiss is one of the activation function that came recently in 2018, and it is basically x into sigmoid beta x. So what happens if the value of beta is very high, then it is going to be very similar to the ReLU. But if the value of beta is smaller, then this is going to be very near to the linear activation function. So that's where this is going to adopt the shape of the activation function based on the complexity requirement. Overfitting and underfitting, so these are another issues which is generally present in machine learning as well as in deep learning. So always, what is the complexity of the data set that we have? We need to match the complexity of our model as well. If our model is basically, if our model is having a higher complexity, then it will perform overfitting, then it will attract overfitting very fast. But if If the complexity of our data set is very high, but the model is low, then it is going to be underfitting, which is basically kind of a inadequate. But if the complexity of the data set that we are handling and the complexity of the model somewhere matching, then we will be able to get a good trade-off between this underfitting and overfitting. So this is again showing this overfitting with respect to the number of parameters. If you increase the number of parameters, then the likelihood of getting overfitted will increase. Then in order to avoid this overfitting in deep learning, there are many regularization techniques. And one regularization technique is dropout, where randomly some of the neurons are dropped, means it is not considered for the computation. Then basically it will act like kind of a symbol of different sub-network, and this is going to improve the generalization ability. We can also include some regularization, like we can include weight L2 weight decay or L1 weight decay, or even we can also perform the early stopping, where we can stop the network early and then we can again start the trading. Batch normalization is also one of the way of performing this regularization, where we want to maintain this Gaussian nature with zero mean, with zero mean and its unit standard deviation of our data that we are handling. If our data is having this Gaussian nature, then we can basically have kind of a smoother training as compared to the data if it doesn't follow zero mean and unit standard deviation. So then what happens, because we have different layers, then this structure is going to be disturbed by different layers. So we can include we can basically do this forcibly by including this batch normalization at multiple stages. So this batch normalization can be inserted even after fully connected or convolution layer or before nonlinearity. So it improves the gradient flow, allows higher learning rates, reduces the strong dependency on the random initialization that we have, and acts as the regularization technique. So ultimately, when we are going to train the model, we need to basically compute the error, and then that is called the objective function or the loss function or the error function. So for classification, we can utilize the softmax, cross entropy. I mean, there are different loss functions available. For regression, we can utilize mean squared error or mean absolute error. So for different problems, we actually have the different loss functions or the error functions, which is going to give us the goodness of our model, and then we would like to minimize that loss function. So here, basically, let me show one demo on this multi-layer neural network. So I will basically just stop sharing from here. I will now share my this browser. So I guess that my browser should be now visible to you.
Yes, sir.
Yes. So this is a very nice tool to visualize many things about these neural networks and do a lot of basically practical things. So we have a lot of controls here, like we can use different learning rates here. We can use different activation functions, like we have tanh here. We can use regularizer like L1, L2 regularizing rate. We can basically have even different classification, different type of problems like classification and relation we can take. And now we can basically build here a neural network. So what we can do? So right now, this neural network is taking the data. So here you can see data is coming from here. So now what I can do, I can introduce some noise in the data such that it should not be very easily separable. So I'm increasing the noise label here. So suppose if I'm gone to 15, you can see at the right hand side here. So what has happened due to this noise label, now some these red points are interleaving with blue points. So basically now this is going to be problematic, or this is going to be now challenge to find out the better and better decision boundary here. So this is a classification problem between these two distribution. One is red distribution, another one is this blue distribution. So here we have these two hidden layers. So first hidden layer is having 4 neurons. I can increase the number of neurons from here, decrease the number of neurons from here. I can increase number of neurons from in the second hidden layers also. Even I can introduce one more hidden layer. So now I got one more hidden layer, and I can increase the number of neurons in this hidden layers also. Suppose I have 4 neurons in the first hidden layer and 6 neurons in the second hidden layer, 4 neurons in the third hidden layer, and then this is the final output. So now I can start the training here, and here you can see learning rate is set to 0.03, and if I will start the training, so what will happen, it is going to show you in the real time that how the decision boundary is going to change on this particular plot. So basically you just focus on this particular plot once I will starting this training. So now here you can see, so this is basically now decision boundary which is being learned here. And now if I will train longer, then what will happen? Now our network will try to modify the decision boundary, this one, into nonlinear fashion in such a way that these red dots should be away from this, or should be basically at one side, and these blue ones should be at other side. So even you can see this some transformations now you can see that is basically happening, and even that is also the indication to the overfitting. And why this is indication to the overfitting? Because it is quite possible that the red dots that we have basically which is interleaved with the blue ones are the noise. And but if our model is having very high complexity, then it will basically overfit this particular thing very fast, and then this noise can be considered. When noise is going to be considered as the part of the data, then basically that is going to be not very good thing. So even I can also show you the difference between different activation function. Like this is tan activation function. So suppose if I do not use any activation function, as I mentioned, if we do not use any activation function, then our how many number of neurons we have in our deep neural network is useless. So suppose if I just use the linear activation function here. So what is going to happen? If I'm using linear activation function, no non-linearity. Now my neural network cannot learn the non-linear decision boundary. It can learn only the linear decision boundary. Because even I have 4 plus 6 plus 4, and ultimately this is going to produce classes here. So 1. So 4 plus 6 plus 4. So this is going to be 15 neurons I have in this neural network right now. But this is going to be useless because even it cannot learn the non-linear decision boundary. And if I start the training here, so you can see also. So what is happening? It is only learning the linear decision boundary. And why it is happening? Because there is no non-linearity. We have the linear activation function. Linear activation function means y is equals to x, means there is no change at all. So that's where this activation function or non-linearity is going to be very important in this neural network. Okay, so let me again come back to this slide. Okay, so I hope the slides will be visible now. So this is about this neural network and deep learning introduction. Now we will move to one special type of this deep learning models, which is called convolutional neural network. And suppose if I have this multi-layered neural network, is it possible to use multi-layered neural network for image data? If I want to perform image classification, is it possible to use this for the image data? So that is going to be one of the difficult tasks, because this network that we have, it requires the data in a vectorized form. For example, here this input layer is having a vector of 3 values, but our input here is not just one vector, it is entire matrix. Then how we can use this image as the input to this particular neural network? So one possibility is we can stretch the pixels in a single column vector, and then we can give that as the input to this particular neural network. But that will be problematic from different perspective, like the number of values that we will have after stretching it will be many. So suppose if you have a typical 256 cross 256 into 3 dimensional image, then the number of pixels is going to be many. It means that the number of neurons in the it means the number of values in the input layer itself is going to be too many. Then the number of neurons in the hidden layer will be it should be even more than that, then how many number of parameters we are going to have. So suppose if you have if you have a 1 lakh number of input values, and you are also going to have at least 1 lakh number of neurons in the first hidden layer, now you can assume the number of parameters you are going to have 1 lakh into 1 lakh. That is going to be very difficult to train this deep neural network model. This is one problem. And another problem, if you just stretch it out, then we are going to lose the visual appearance in the 2D. It will become 1D information. Then we are going to lose the important information. So then the solution is going to be the convolutional neural network. Now, this is also termed as CNN or Coronate or DCN. So there are many basically names people use to refer this convolutional neural network. And convolutional neural network works based on these two underlying concepts, which actually facilitates this entire convolutional neural network. It's called local connectivity and weight sharing. So now let's have a look what is the meaning of local connectivity and weight sharing. So what neural network we have seen so far here in this particular lecture, that we have seen as with the global connectivity. Because even if you can remember, I stressed with this particular thing that a neuron in one layer is connected with all the neurons in its previous layer, because that was the global connectivity. So here, suppose if this is my input layer, this is the hidden layer. So a neuron in the hidden layer will be connected to all the neurons in the input layer. It means that if I want to compute the number of parameters here, then the number of parameters is going to be basically in this particular case 1, 2, 3, 4, 5, 6, 7. So 7 for one neuron in the hidden layer, and we have 3. So 3 into 7, 21 parameters we are going to have. But if we talk about the local connectivity, so in case of the local connectivity, a neuron in any hidden layer will not be connected with all the neurons in its previous layer. Rather, it is going to be connected only with the few neurons which is in its local proximity or in the local neighborhood. So if you see, if I'm considering the local neighborhood as 3, then this neuron is connected with only 3 neurons here. The second neuron is also connected with only 3 neurons. So in case of the local connectivity, now how many parameters I'm going to have? So 3 plus 3 plus 3. Now I'm going to have only 9 parameters. So now you can see the number of parameters in the local connectivity is going to be reduced drastically from 21 to 9. Similarly, we can also perform the weight sharing. So this neural network model that we have seen so far, they don't use weight sharing. What is the meaning of weight sharing? Suppose if I have 3 neurons in the hidden layer, then each neurons are having its own weights, which is different from basically different neurons. Like if this is W1, W2, W3, then for the second neuron, the weights will be different, like W4, W5, W6. For the third neuron in the same layer, weights are different. However, in case of the weight sharing, the weights for all the neurons in a given layer, that is within a layer, it's not basically between the layers, that is within the layer is going to be shared. It means if the weights used by the first neuron in the hidden layer is W1, W2, W3, then the same weight will be also used by the second neuron, third neuron, all the neurons in that layer. So it means that again, the number of parameters are going to reduce to only 3. So now if I utilize weight sharing and local connectivity both, then the number of parameters are reduced from 21 to 9. It means 21 to 3. It means that our model is going to have less and less number of parameters by utilizing these two concepts. And why it is required? Because the kind of data that we aim to deal here, that is high dimensional data. Whenever we are talking about images, then you will talk about how many number of pixels you have in the image. So 256 into 256 into 3, that is the dimensionality of the data that we are handling here. And that is very high dimensional data. That's where if we do not utilize the weight sharing and the local connectivity concept, then it is roughly impossible for our existing these computational resources to perform the training of any deep model. So now any convolutional neural network is going to build with different layers, like we are going to have convolutional layers. These convolutional layers will utilize the weight sharing and local connectivity. And we will have the activation functions like ReLU layers. We will also have downsampling layers like coding layers and some fully connected layers at the end. And ultimately we will have the basically classification layer finally. So these are different layers. We have already talked about nonlinearity layers. Now we are going to see about convolution layer, polling layer, and majorly these two layers we are going to see in convolutional neural network. So the most important layer in any convolutional neural network is the convolution layer. And convolution layer is a very simple layer. If you know a little bit about the filtering concept of image processing, then this is very easy for you to understand. Even if you don't know, then already it is easy to understand what is the meaning of this convolution. So don't get confused with the word convolution here. In deep learning, we use the word convolution, but actually we perform the filtering. That is the basically underlying implementation that is used in this convolution layer. So what we are going to have here. So suppose if I have an image and my image is having the dimension 32 cross 32, that is the spatial dimension. And if it is a color image, then the depth is 3, means red, green, blue, 3 channels. Then the resolution of the image is 32 cross 32 cross 3. So now I'm going to have a filter here, and this filter will also have some spatial resolution like 5 cross 5 in this example. And this filter will also have more than one number of channels if we have more than one number of channel in our input. And in fact, the number of channel in the filter will be exactly same as the number of channel in our input. Our input has here 3 number of channels. So our filter will also have exactly 3 number of channels, and the spatial resolution is 5 cross 5. So now what we are going to do, we are going to basically we are just going to use this filter as a mask, and then we are going to superimpose with our input, and after superimposing, we'll perform the dot product. So dot product means the multiplication of the corresponding values of our input and the filter, and then just taking sum of all these products. So after doing this, we will produce a single value as the output, means just superimposing at one place and performing this dot product will produce a single value in our output. And then after that, what we will do, we will take the same filter, and we will just stride it over the entire spatial resolution of our input image. And if we just stride it over the entire spatial resolution, so here you can visualize in this particular figure, so how actually we can do this. So now you can see this is basically a 3 cross 3 cross 3 filter is used. So once we will basically start from top and left corner, we will perform the dot product, one value will be generated. Now we'll just slide it by one position, then again one position, again one position, again one position, again going down. Then we will slide over the entire spatial resolution, and we will perform this dot product every time. Then ultimately we will be able to produce the entire channel as one channel as the output. Now question comes that what is this filter here? So this filter is actually nothing but it is going to have some values, and those values are basically treated as those are actually parameters. Initially, we will initialize those values randomly, but we are going to update those values using this gradient descent optimization technique that we have seen in case of even deep neural network. So if we are not using some padding, then our spatial resolution may decrease, because when we are going to superimpose, we cannot superimpose with extreme left and top corner because we do not have sufficient neighborhood. Then we may have to leave some of the rows and columns from the borders if we do not have the padding. But if we have the padding, then even we can utilize that. So, but in this particular example, padding is not used. That's why this spatial resolution is reduced from 32 cross 32 to 28 cross 28 in the output. But we have only one channel produced here. Similarly, because this filter is having the values which is randomly assigned initially and then it will be updated, then instead of one filter, even we can have multiple filters. I can have one more filter, and that filter will be initialized separately, and then it may compute the different feature. So it means that if I have a second filter, then I can perform exactly the same task with a second filter. I can produce one more channel in the output, and that is going to be basically our second channel. Similarly, I can have one more filter that is going to produce one more channel. One more filter will produce one more channel. So if I use 96 number of filters, then I can produce 96 number of channels. So now still you might have a question here that why to use 96 filters? And what might be difference between these 96 channels that we have here. So now you can understand this particular thing, that why we need these multiple filters from a very simple example. So suppose if I have an image, and I want to perform this facial expression recognition problem, that a particular person is in which mood he is, happy or he is sad, means whatever is the expression that he has. Now, in order to do that, now my image is having the face here, means my input 32 cross 32 cross 3 is a color face image. And now I have a filter here. Now, this filter is designed in such a way that it is going to produce the higher output, means it is going to be activated. It is going to produce the higher output when it is going to see, kind of a happy thing, whatever is the happy visual characteristic that we could get near to our eyes. So it means that this particular filter is, suppose it is going to extract the important features, or it is basically going to generate higher output to those locations, to those regions in the image where we are getting such type of features. Always, what is meaning of filtering? The meaning of filtering is, filter is having some characteristic. Filter is trying to extract some kind of information from the from our input, and it will discard the rest of the things. And basically, suppose if my filter is designed in such a way that suppose it wants to extract kind of a horizontal edges, then what will happen? It will produce the higher output, means the values at the higher side in our final output if edge is present, if such horizontal edge is present in our input image. And for rest of the pixel values, it is going to produce near zero values. That's what is the meaning of filtering, because we are basically using the same mask and we are just sliding it over the entire spatial resolution of our input image. So now what is going to happen here? So if I'm going to perform this particular task, and my one filter is, suppose if it is learning the characteristic, it is going to produce the higher output if it is producing the visual appearance in the happy nature that is near the eye region. But is it sufficient to take the decision just based on that someone is happy? That might not be sufficient. So what might be, but at the same time, rest of the information is discarded in this channel. Means suppose if the first output channel is produced here is actually having the higher values only to those spatial regions where we are basically getting that type of visual appearance, which is characterized by this particular filter, and rest of the information is lost in this particular channel, in the first channel, then that is not going to be sufficient. Based on that, we cannot basically take the final decision, because we should also look some other important features. We should also look that, okay, what is the visual characteristic, what is the visual appearance that we are getting for even some other expression, because even we can have kind of a ambiguous visual appearances for different these emotions at a particular location on our face. Then in that particular scenario, we should also extract some different features. So that's where we can have now one more filter. Suppose another filter is basically looking for the information that, okay, what is the visual appearance for the happy, that is, let's say, near the mouth region. So like that, these different filters are going to act as a feature extraction of a different characteristic from our input image or from our input. So that's where we just one filter is not going to be sufficient. We need more filters. Again, this is going to be a hyperparameter, and it is again debatable that how we can find out the right set of values, how many number of filter we should use, how to find out. So all these things are going to be much more practical scenario, where if we are designing convolutional neural networks, if you are solving a lot of problems, then what data set you are using, what is the complexity of your data set, and how deep network you have. So based on these things, slowly you can learn these kind of a tricks that, okay, how many number of filters we should use. So again, this is dependent upon the complexity that you can sustain, and that basically you can train using the computation resources that you have in your hand, or also considering the complexity of the problem that you are trying to solve. So based on these factors, this is again very subjective to design these basically hyperparameters, that how many number of filters, or what should be the filter size, all these things. So here you can see what I was talking. So suppose if I have an image like this here, if I have a filter, so this is a filter mask here, And this mask, if I am just going to slide it over the entire this image, then it is going to produce a feature map. So this is the feature map that is computed by one filter. Now I can have another filter, and this filter is basically extracting this feature map. And now you can see the feature map that we have extracted using these two filters might be basically exploiting some different visual characteristic. Similarly, I can have any number of filters. If I use k number of filters, then basically I can extract k number of different and distinguishable these feature characteristic from our input. So this is exactly the same thing. So suppose if we have three channels, red, green, blue, then we are also having three channels in our mask, and just doing the dot product of corresponding values and adding with the bias term, this will produce one value. Then we can slide it, and again we can produce another value. We can again slide it, we can produce another value. So now it's not just about one layer. As we mentioned, a deep neural network is having many number of hidden layers. Similarly, in convolutional neural network also, we can have a deep convolutional neural network where we can have even many number of convolution layer as well. So now, if I want to use a convolution layer in the middle, means not just in the first layer. So first layer is convolution layer. After that, we can have activation function, then batch normalization, and even we can have any other dropout layers. These things we can utilize. But if I want to have one more convolution layer, then how I can design that convolution layer, which is taking feature itself, the activation map itself as the input. So for example, if this activation map having the dimension 28 cross 28 cross 96, if I want to use a conv layer on top of this, then that con layer is also going to have the filter. So spatial resolution 5 cross 5, 3 cross 3, 7 cross 7, we can have any spatial resolution. But question comes, how many number of channels we should have in the filter? Now, the answer is number of channels should be same as the number of channels that we have in activation map. Why? Because when we are going to do the dot product, we will do the dot product across all the channels. Then we should have exactly same number of channels in our filter also that we have in our activation map. So again, using this 5 cross 5 cross 96, this is our basically dimension of our filter. If you just do the dot product of this entire block, now this is volume. This is volume of size 5 cross 5 cross 96. Same volume we will take from our activation map also doing the dot product. It will produce now one value in our output. Exactly same concept as used earlier. Now again, sliding over the entire spatial resolution, that is 28 cross 28 here, will produce one channel in the output. And again, because we are not doing any padding, then this spatial resolution is dropped to 24 cross 1. And we can increase the number of filters now. Suppose if I increase the number of filters to 128, now I can produce a deeper activation map, and it is having a dimension 24 cross 128. Similarly, now I can have any number of convolution layers that I can include. So for example, initially 32 cross 32, then 28 cross 28, 24 cross 24. Suppose if I use one more convolution layer, it will become 20 cross 20. If I use one more, 16 cross 16. So what will happen? So if we do not use the padding, then the spatial resolution of our activation map is shrinking very fast, and we cannot build even a convolution neural network with 50 layers. What is going to happen after going for six layer or 10 layers? Our spatial resolution will collapse. So that's where this padding is going to be one of the important things that we will see shortly. But any convolution layer will have these four important characteristics. Two, we have already seen, local connectivity and weight sharing. We can also have a look at how this CNN is ensuring this local connectivity. So what is happening? When we are performing this dot product of kernel, means when we are basically just, when we are superimposing and then doing the dot product, then actually we are computing one value, and that value is going to be at the location which is at the center of this particular location, this mask where it is currently superimposed. So it means that this one value which is computed in the output channel is based on not the entire input, it is only based on this 5 cross 5 if our resolution is 5 cross 5 for the filter. So, and it means that this is basically utilizing this local connectivity. What will be the global connectivity? In order to compute one value here, if I perform the computation on the entire input, then that is going to become the global connectivity. But global connectivity will be horrible in convolutional neural network because our image data is very high dimensional. Weight sharing is also utilized here because the same filter we are just sliding over the entire spatial resolution. Means if I compute any value, in this particular output channel, then I have used exactly same filter everywhere. What is changed is only the input region where I'm using this particular filter. So it is basically exploiting both the concept of local connectivity and weight sharing. At the same time, it is also very much flexible and adaptable to use any number of input channels, and it can also produce any number of output channels. If I want to use, if I have the input with 96 number of input channels, then my filters can also have the 96 channels. It can accommodate any number of channels in the input. Similarly, if I want to produce 128 channel in the output, then I can use 128 number of filters. Then each filter can produce one output channel, means 128 filters can produce 128 number of output channels or output maps. We can also compute what is the output dimension based on what is the input dimension that we have and what is our stride and what is basically these hyperparameters. So using these hyperparameters, we can compute the output dimension as well. So, and this is a very simple example, a very simple formula to compute n minus f divided by stride plus 1 means what is the n is the spatial resolution of input, f is the spatial resolution of the filter, and stride is means by how many position we are shifting the window. So we have seen by one position, but even we can change the number of position by which we are shifting the window. Then what will happen? The spatial resolution can decrease even in a faster manner. So we can also perform the padding. So padding means just padding by the zero values. There are many padding mechanisms, but generally padding by zero is followed in common practice. So what is going to happen? Suppose if my filter is 3 cross 3 dimensional, I want to produce same size output, I will perform the padding by 1, means 1 in all side. If my filter dimension is 5 cross 5, I want to retain the input, I want to retain the spatial dimension of the activation map, I will do the padding by 2. If my filter dimension is 7 cross 7, I want to retain the spatial resolution of activation map, then my padding will be 3. So like that, we can perform the padding. So this is basically the formula. I will share these slides. Maybe you can have a look on these formulas later on, as now we have very less time to close this. The other layer which is very common is the pooling layer. So it is also required that we need to reduce the spatial resolution when we are increasing the number of channels, because with the higher spatial resolution and more number of channels, again it will become computationally very complex to handle. So what happens when we increase the number of channels, then we want to reduce the spatial resolution, and this pooling layers basically plays an important role to reduce the spatial resolution. Max pooling is very common in practice. So in case of the max pooling, what we want to do, if we take a window size of 2 cross 2, then I will just only take the maximum value of these 2 cross 2 window. I will throw out rest of the values. So basically, using this mechanism, I'm going to retain the maximum values in the local neighborhood and throw out the remaining values. And why it makes sense to do that? Because it is related to because this max pooling is always utilized on top of the convolution layer, and convolution layer is based on the filtering concept. And in case of the filtering concept, we are producing higher output to those locations where we are getting the similar characteristic in our input, and we are getting smaller values if such characteristics are not available in the input. So if you are throwing away the smaller values, then this is not going to basically problematic, because the information which is going to be lost here will be very minimal, and even most of the time it is irrelevant information which is going to be lost. So again, we can also compute the dimension of the pooling layer. Fully connected layer is the same as the as we have seen in case of the deep neural network, where one neuron is connected with all the neurons in the previous layer. So some fully connected layers we also use in case of the CNN towards end of the network. And one fully connected layer is compulsory to have that will basically map, that will basically produce the classes scores for all the classes. Activation functions we have already seen. Objective functions, there are different objective functions based on our loss layer, based on different problems that we are solving. So everything combined here. So we have the input image, then we can basically learn the filters, which is going to extract the important features. We can have the non-linearity on top of that. Then we can have the spatial pooling, which is going to reduce the, which is going to basically reduce the spatial resolution. Then this is a feature map. We can repeat this process multiple times, and ultimately we can have this network after repeating this convolution pooling, and these activation functions, and some basically other layers like batch normalization, dropout vectorization layers. So ultimately, we can have large fully connected layer, which is producing the class scores. That is basically the probabilities for the different classes. Then based on the highest probability, we can take the decision. So this is about CNN, and the CNN started gaining a lot of popularity after 2012 when the first model basically that became very popular, that was AlexNet, that owned this ImageNet challenge in 2012. And the key growth that has driven this entire deep learning is nowadays availability of the high-end computational resources like CPUs and large-scale datasets like this ImageNet dataset. So this is the growth on this ImageNet challenge, that the model basically in 2012 we got 16.4, that is error rate, top 5 error rate, and even in 2017 this error rate was reduced drastically to 2.251. However, in 2012 itself, the best model, that is non-deep learning models, its error rate was 26.2. So basically there was a huge gap between the best non-convolutional neural network model and the convolutional neural network model in 2012. And that's where basically people started giving more attention to this convolutional neural network, and main solved for images and videos, they are actually utilizing these convolutional neural networks as the backbone. So these materials which is presented here, they are taken from the many sources. Even it is also possible that some original sources might not be cited here, but that might be unintentional. But still, I have tried to cite most of the references at the appropriate places. So these are some references. Resources. So I will skip these research areas of mine. Okay, so that's it about this particular talk. Now, if you have any questions, then I would like to take it.
Yeah. Any queries for the from the participants? So I repeat, if you have any queries, please ask the resource person, Dr. Shivanam.
So even if someone has any doubt, then even they can ask later, or also that's not an issue. You can directly send email to me, or even you can send email through Chandra sir. That's not an issue.
Something.
So if the input images contain much background data, CNN will be appropriate to use to filter the region of interest? Yes, it will be useful. And in fact, you can utilize attention in deep neural network in convolution. Attention is one of the recent development which can give more focus to only the important regions based on your problem, and can discard rest of the background. Can we implement CNN for contrast enhancement problem? Yes, you can. You can do that. In fact, many CNNs are being developed basically for the image enhancement. That includes even contrast enhancement, noise removal. There are many such basically applications. But you should have such data sets. If you have some data sets for that, then you can do that. What type of filters we should go for? You don't have to design filters by yourself. You can only just mention that what is the filter dimension. Then it will automatically learn the values of those filters.
I don't think there may be any other query. And if you have any queries also, you can mail to sir. And I'm sharing this PPT. I will communicate the slides to all of you. And thank you very much, Shivram sir, for
Thank you, sir.
For your session, which has given an insight on the complete the transformation or the paradigm shift from machine learning to deep learning, and in particularly the convolutional neural networks in detail with the nice diagrams. So thank you very much. And,
okay, sir. Thank you, sir.
Yeah. So we are done for the day, and tomorrow morning we start the session. Again, Dr. Shivram is going to deliver the session on recurrent neural networks.
Okay, sir. What is the starting time, sir?
It's at 9 o'clock.
9 o'clock. Okay, fine, sir.
I think
okay, sir. So thank you very much. And now I will leave.
Yes.
We have some other urgent meetings.
Yeah,
So
sure.
Thank you very much, sir.
So we are done for the day, and tomorrow we'll continue with the recurrent neural networks, and then we have another session, the next session, the practical approaches on how to do the implementation of convolutional neural networks and so on. So this is what actually the plan was, start from the basics of the data science and then explore some sort of machine learning simple classifiers, and then elevate the level of learning towards machine learning, so that the best possible extent we can give it in these 5 days, so that upon interest, each and every one of you can further have a deep dive into their own interested topics and do some good work. So with this closing note, we close the session now, and I request all the participants to be in time, especially in the morning hours. That if you are join in the link at least 5 minutes before itself, I thought that there will be so lot of congestion, but there was no congestion at all. People were hardly 5 to 10, and slowly it was increasing as the session was progressing. So that please, I request all of you, at least for the last 2 days, you be in time and learn more from the resource persons and keep interacting with the resource person. Thank you.